Hello, I am Dr. Jude Osara. In this video, I demonstrate a lubricant analysis software based on the degradation entropy generation DEG methods. A breakdown of the DEG methods can be found in my previous video. If you rub your hands together, you can feel your palms getting hot. This heat is generated by the frictional force between the inner surfaces of your hands. If you rub faster, they tend to get hotter faster. If you push them together harder while rubbing, they also get hotter faster and may eventually break the skin if continued long enough. Similarly, in machines and vehicles with moving parts, friction, in addition to dissipating energy and generating heat, causes interfacial wear and hence degradation of components. To mitigate these effects, a lubricant is applied between both solid boundaries. The relative motion or shear motion between the boundaries induces shear stress in the lubricant, which is a function of the lubricant material properties and how fast the boundaries are moving relative to their distance apart, which is known as the shear strain rate. Over time, the stress accumulated in the lubricant is such that the lubricant is no longer able to reduce friction effectively. Sudden failures of lubricated interfaces can be fatal, as in helicopter applications, among others. Hence, the need for an adequate, consistently accurate analysis approach cannot be overemphasized. The DEG Universal Lubricant Analyzer characterizes all lubricants using unsteady, in situ, and even severely abusive data, consistently at 100% accuracy. Here is the DEG Universal Lubricant Analyzer 1.0 Alpha. Before we perform an analysis, first a quick walkthrough. The menu and toolbars are two typical components of a program with a graphical user interface. Here I have included the file menu with some familiar submenus for file operations, the analysis menu for analysis-specific operations, and the help menu for documentation and other program information. The toolbar buttons, as usual, are faster ways of performing the same functions in the menu bar. Hover the mouse pointer over each tool to see its function. New file, open an existing file. Save project, open an existing settings file. Enable run settings, used to activate the grayed out options required to run the program, only useful under certain circumstances. Exit or quit the program, open the help documentation, and here is the program info or about button. On the left side here is the project tree. Currently, it only highlights which section is active: input, settings, or run. Below that is the details panel. Here I output analysis information and recommendations as the user performs each step successfully. Now onto the main panel where most of the user interactions take place. This text box holds the project name, which is also its file name. A .deg extension is appended when the project is saved. In the input section, the user selects lubricant type, classification, material properties, CSV file with time-based data, and control type. After specifying the required inputs, use this button to pre-process. A successful input pre-process will output results in the provided text area below. The pre-process step reviews the inputs for validity, including the CSV data file, and outputs test duration, minimum and maximum values of each variable in the data file, and so on. Under settings, the user specifies analysis type. Use analysis parameter to choose the degradation measure. This is usually the system response parameter during loading. For example, stress is often the response parameter for strain-loaded systems, and strain is often the response variable for stress loading. Others include viscosity, penetration depth, and so on. Here the user can choose to output only the DEG coefficients via the basic option, or all analysis results via the detailed option. Use this to save the settings and prepare to run the analysis. The program creates a settings file with the project name and stores the settings in it so the user can reuse the settings whenever needed. To load a saved settings file, use the wrench tool on the toolbar. Under Run, the user decides if they want to create and/or save plots. Sometimes a user might want to view plots without saving them, for example, after changing a setting, material property, and so on. Use the oversize button to run the analysis. For this demonstration, we will use the NAGI4 grease on which I performed tests and measured data. This type of grease is typically used in heavy load applications, like helicopter rotor bearings. It is of relatively high shear strength and consistency. First, let's take a quick look inside the CSV data file. The analyzer program expects 4 data columns, with the expression of isothermal analysis, time in hours, shear stress in Pascal, shear rate in per second, and temperature in degrees Celsius. We start by clicking the New Toolbar button. Enter a project name, then select a working directory. To use the current, also the most recent directory identified by the operating system, click Cancel. The chosen name automatically appears in the appropriate text box. Pay attention to status updates in the status bar as we progress through the steps. Select grease as lubricant type. The classification list is populated depending on the selected lubricant type. For example, if I choose engine oil, the classifications are SAE-based engine oil classifications. SAE is the Society of Automotive Engineers. For now, let's go back to grease. Now the classification is for grease based on NLGI groupings of grease consistencies. NLGI stands for National Lubricating Grease Institute. Here I have set up default material properties for a few of the lubricant classes. Select Custom and use the Edit button to specify new properties. I will increase the density here to the actual value for this grease. If available in a CSV file, properties can be quickly loaded using this button. Down here are parameters needed for thermal analysis. The user does not need to know these to perform the regular utility analysis, but they are required for the thermal analysis. The values here are from my grease research. Click OK to apply the user-defined values. The control type is the load parameter that is controlled, typically held constant during the test. Here I have given the option to perform an isothermal analysis, which should only be performed in the absence of temperature data. However, while I do not recommend it, the user can also use this option to replace the temperature data in the CSV file with a specified constant temperature. Note that the DEG methodology's strength is in its ability to perform consistently accurate analysis of a system in unsteady operation. Prevalent analysis approaches are already suited for steady-state isothermal analysis. With the DEG, the system's natural response to loading is used to characterize the system without assumptions. Isothermal analysis is very restricted and relatively simple in comparison with what the DEG excels at. I have temperature variation data, so we are not interested in isothermal analysis at this time. Next, we select the CSV data file. Now let's pre-process. We get an error message alerting us to our wrong choice of control type. The program examines every column in the data file and checks for typical differences in controlled and spontaneous parameters. In this case, the test was strain rate controlled, so we need to select strain as control type. Now we can pre-process successfully. Note the new information in the details area. It is important to review the pre-process results to ensure there are no anomalies. You can see here that my strain rate is constant while stress and temperature varied with time, verifying that the experiment was strain rate controlled. Input issues that do not obstruct analysis but may impact results interpretation are included in warnings. For example, if isothermal is not selected but the temperature column in the data file contains constant values, a warning would appear here. For our first analysis, we select utility. We will discuss other options subsequently. Note that when the control type is chosen, that parameter cannot be used as a degradation or transformation measure. In other words, the analysis parameter list box, which is the transformation measure here, populates based on the control type chosen. With strain control selected, we can use stress, viscosity, or penetration as analysis parameter. Stress, strain, and viscosity are fairly well known in solid and fluid mechanics. Penetration is an ASTM and NLGI parameter that evaluates grease consistency by measuring how deep a cone of specified dimensions and weight would penetrate a sample of the grease. Let's start with stress. Here we will leave detailed selected to get all output results. Then we save settings. If there was no project name specified, we will be allotted to enter a name at this point. We'll leave these two selected and run. Now let's do some results interpretation based on the DEG fundamentals we reviewed previously. Before we review the plots, let's see the analysis results in the output window. Here we see stress-based analysis results, DEG coefficients, dissipation factor, entropic efficiency, and average strength degradation. We will not go into the meanings of these right now. Down here, I have added notes that prescribe favorable and adverse trends. Here we have 4 figures. Upper left presents plots of measured stress and temperature. The upper right figure shows entropy components. The blue line is the load or boundary entropy, the desired or useful component, while the red line is the MST entropy, the adverse dissipative component, as discussed in the previous video. The DEG domain here linearly relates the chosen measure to entropy generation components via the DEG plane. As I explained previously, a shallow DEG domain via a low MST entropy indicates lower dissipation and hence degradation rate. The final figure here overlays measured and phenomenological shear stresses and the dissipation parameter obtained as the difference between cumulative versions of both stresses. These plots here pertain more specifically to monitoring and optimization, which are outside the scope of the current discussion. After reviewing the results, we can now save the project. Okay, to demonstrate a user choosing their own degradation measure, let's repeat the same analysis using the different analysis parameter. First, I'll add P to the project name, then select penetration here. I obtain the equation for penetration change as a function of accumulative entropy generation from Riza Soltani and Konsari's paper. Now we can save these new settings and run. Top figures are the same as previously seen in the stress-based analysis. The bottom 2 figures show penetration as degradation measure. Note increasing penetration, which indicates loss of grease consistency as entropies accumulate. In the analysis results window, we can see values of the DEG elements for the penetration-based analysis. Save project under new file name. A new paper we recently published uses the system's material properties and temperature profile during loading to analyze the system's degradation. To avoid overloading this presentation with new content, I will not go into the conceptual breakdown of this particular approach. Suffice it to say that this particular approach is useful for thermal design and optimization. The characteristic elements remain the same, and even the result interpretations are similar, but not the same. Let's perform a thermal analysis and compare the results to a utility analysis. We will use the same input selections as the utility analysis. First, let's add a T to the file name, then select thermal. Go back to Material Properties, select Custom, and click Edit. Here we want to enter some dimensions needed for our one-dimensional lumped thermal capacitance heat transfer analysis. I have set this up for a cylindrical profile, which is the most common profile in lubrication analysis. It can be easily adapted to a planar profile if needed. Again, these values are from our grease paper. Select stress as analysis parameter, save settings, and run. Overall, this looks just like the previous utility results, and that is because it's still the same methodology, only the entropy generation has changed. Except for the first figure showing the same measured data, the analysis plots are different. The second figure here shows heat transfer and heat storage entropies based on the thermal entropy balance. The important thing to note here is that similar to the utility approach in which the MSG entropy is adverse, the heat storage entropy here is also adverse and should be minimized for optimum performance. The heat transfer entropy here is comparable to the load entropy in the utility analysis, as they are both boundary interactions, which means they are external to the system. Here the thermal entropies are linearly related to the shear stress. And here we have the DEG coefficients and others, just like the utility analysis. Save the project file. We can repeat the thermal analysis based on penetration as well. The last analysis type I want to demonstrate is the comparative utility analysis using the multiple option. This can examine two different lubricants on the same set of axes, or one lubricant subjected to different load types. Here we will process two different grease types simultaneously and compare their performance and degradation tendencies. For the second lubricant, we will use NLGI2 grease. This is a common multi-purpose automotive grease with lower shear strength and consistency than the first grease, which is NLGI4. Add M to the project name, then select Utility Multiple checkbox. A dialog box opens for the user to enter the second lubricant details. Specify a name, choose Material Properties. Here I have entered Material Properties for the second grease type. Then select CSV data file, save settings, and run. Now we can see data and results for both greases plotted on the same sets of axes. The dashed lines represent the second grease. Here you can see the lower strength grease with lower resistance to shear has lower stress and temperature response to the strain rate loading as the high strength grease, represented by the continuous lines. This response is transferred to the entropies as well. Down here it gets more interesting as we get to directly compare the dissipative tendencies of both grease types. Here you would notice that even though the test durations are relatively similar, the dimensions of the DEG geometric elements are very different. The lower strength grease has much less available energy than the high strength grease, but also dissipates less energy. The lower right plot is the normalized DEG domain, which I nicknamed the evocati, because it should not be created without first creating the regular DEG domains. Again, to avoid content overload, I will leave the evo for future discussion. In the analysis results window, we can see results for both grease types for direct comparison. Save the project file. Now if we close these plots and need to retrieve a saved project, we simply open the particular project file we are interested in, and all the user inputs and results including plots are open for viewing and modification. Currently, the user can only save PDF and PNG files, so these cannot be interacted with as when they were originally created. But without modifying any of the settings, we can quickly recreate an interactive plot if needed. In this video, I demonstrated the DEG methodology's purely physics-based analysis approach. The results are the system's natural response to loading. So if the analyst can identify an optimum design, they can benchmark other designs against it. There are several material properties that can be modified to obtain improved performance and characteristics. Also, manufacturers and some consumers can compare components from various suppliers and choose the optimum product with more certainty. Other immediately available applications I have not discussed in this video include failure prediction, real-time monitoring, and optimization. If interested, please stay connected with our publications on ResearchGate and other websites. I often post updates and new research work on my personal LinkedIn profile as well. Thank you very much for watching. Stay curious.